A bit over 3.5 years ago, I released this video, which was meant to be the start of a mini-series on designing my own yaw probe. Now, because this was being developed here, instead of using F1 technology strictly, it had to be cheap. So nothing like a multi-hole probe or anything like that. It had to be a basic conventional airfoil profile that could be 3D printed and pitos that could be put together with cheap off-the-shelf components. And today, we finally have some progress to show on this. Shortly after that video, I had a helpful viewer email me and suggest that I try a microcontroller different to an Arduino, a board called a Teensy. This board would be smaller and have much more processing power, and this led down a little bit of a rabbit hole as to what else I could potentially put on this yaw probe to log at the same time as the actual aerodynamic parameters. And as with any good rabbit hole, that of course leads to a bit of a spending spree.
Me for granted and you know I'm leaving. I'ma take what's mine with the webs I'm weaving. I could take this crowd from seeing to believing. Got a taste for blood and my tongue keeps bleeding.
That expenditure all occurred at the start of 2021. Since that point, I've had what's largely been a mess of wires sitting on the desk behind me. I've been able to physically rig things up, but I could never quite get the whole system to work. Most of this was a bit of a software limitation on my end. I couldn't really work out how to code everything well. I'm not the strongest coder out there. However, more recent advances in technology, such as more advanced ChatGPT versions, helped me out quite a lot here and made it so I could actually make this project work. With that in mind, I managed to actually find some time to set aside for the project in the last couple of months, and that allowed me to actually get a system that worked and logged everything from a whole bunch of different sensors. Once I was able to get the RASNES functioning as an actual unit, I was able to put everything together onto a small prototyping board and then start soldering up everything to miniaturize my entire device. Because it was going to be critical to have everything in a way that was reliable so that under the vibrations of on-car use, the device would actually hold together and not just fall apart. And also it had to be very compact because I wanted to fit everything into a very small probe. So I mocked everything up, blue tapes down the boards that I wanted to hold onto the board, grabbed all the soldering kit I needed off someone I knew who was throwing it out, and then set to work with soldering together this little board. Basically, I soldered on all the headers to allow me to fit my Teensy onto the board and then branch it out to individual connectors that would allow me to connect up each sensor. I then just finished a few little traces with bits of wire that I soldered onto the board, and then I had something that was much, much smaller than my original breadboard and wiring setup. After checking all the connections on the board, I knew that I was good to go and could start using this to actually play around with. Now, I could have done this whole setup as a custom PCB, which would have been significantly more compact. However, that's quite a bit outside my electronics skill level. Already, this project is far more electronics than I've ever done in my life. And as a result, I feel like a lot of people watching this video who actually know what they're doing with electronics probably feel right now how I feel when I watch someone try to do a video on aerodynamics. So what we have here is that we've got in the center, we've got this board, which is called a Teensy. It's basically a microcontroller, and then we have a few peripheral devices connected to it. So what we have here is that we have this here, which is an atmospheric sensor. So there's basically an air sensor that does your humidity, your temperature, your pressure, and any VOC concentration there. Not that we need VOC, but anyway, I just got it all on one little board that can bolt in. Over here, there's an IMU. So this can measure our accelerations. So there's obviously going in on a race car. Not every race car is going to be logging acceleration, or we'd have to pipe it in by CAN bus, which means we'd have to wire this in, and that's a little bit more of an ordeal. So anyway, it's a handy thing to have so that you can know how hard the car is cornering or braking or accelerating at any given point in time. Then we've got the GPS unit over here. So there's just a little GPS brick. That's to give us our GPS speed and location on track. So obviously that's a little important bit. And then we've got a few different pressure sensors hooked up. So this is just an analog pressure sensor over here. This is a digital pressure sensor, DLVR over here. This is another digital pressure sensor over here. Now, the way that this is all configured is to run through what's known as I2C or I2C. I'm not sure what the correct pronunciation of it is, but basically it's a digital communications bus. And the idea is that I have two I2C buses on this particular device. One is running at 3.3 volts and one is running at 5 volts. So some of these devices, these digital devices, are only set up to accept a 5 volt signal. Other ones will accept 5 volt or a 3.3 volt signal, and some will only accept a 3.3 volt signal. So as a result, I've had to split it up a little bit. Now, I think if I was a little bit cleverer around here, I probably could have gotten everything to work on 3.3, which I'm going to have to do in the future because they don't actually make this board anymore. You need to update to a new board that doesn't take 5 volt, it only takes 3.3. So we'll need to upgrade that. But in the meantime, basically, we've got on this side of the board over here, this is all 5 volt power. It's a 5 volt power rail that I've then gone underneath and I've basically cut it off from the forward portion. So it's electrically separated from this bit here, which is our 5 volt I2C bus. Now between these two bits, you'll see these two little resistors in here. Basically, the way that this I2C system works is that these signal wires are constantly draining lines, so it's going to sit up at 3.3 volts and then these signals are going to drain to ground. And so in order to get the signal back up, it needs to be lifted back up or pulled up using what's known as a pull-up resistor. So we've got one set of pull-up resistors over here for the 5 volt bus. The 3.3 bus, there's only one item on the 3.3, it's just the DLVR. And that particular item is going directly off these pins for teensy in there. And then the resistors are actually in the central channel. Just see them in the center there. They're the pull-ups. They're actually going from the 3.3 volt power, which is over here, and running along in the middle to get to pull up that little bus there for the communications there. And then the 3.3 volt power supply is over here. I'm taking power off this pin here. I'm taking ground off the main device pin there. The last little bit is the GPS, which does not run off the I2C link. That's on a TX-RX system, which I think is technically what a serial link is. And so basically this wire goes to this particular comms link here, and then it's got a 5 volt supply off the 5 volt rail over here. Now all these connectors are all unique. We've got a 3 pin for the TX-RX, the 5 volt and the 3.3 volt power supplies, the different size connectors, so that there's no chance of cross-plugging and potentially overvolting some device. Again, you could avoid a lot of this problem if you instead decided to make everything 3.3 volts, which again, I think that in the future, if I was doing this again, I would try a little bit harder to get everything to 3.3 volts. Basically, it's all mounted to this solar board that's like a breadboard style layout. Please forgive my soldering, I am but a rookie, but basically I've soldered along all these traces that go sideways along here. Makes your life nice and easy because you can just go off pins, and then you've got the rails here and there that you can use for hooking up to power. Over here on the DLVR, I've also made a little breakout board from a similar type board. I think it's called a Vero board normally, and you can see I've just gone and removed the center of the trace through there, and you've got the pins over there where I've connected this connector on. So this is just my own little homemade breakout board for this sensor. All the other sensors came on their own boards, which obviously makes life nice and easy because all you got to do is just terminate the ends with some crimps and then you're singing. So anyway, we're going to get all this, we're going to work out in CAD and we're going to mount it into the yaw probe, and this is going to be our fundamental logging and data acquisition system. So now we've actually got the logger rigged up. So basically there's all the electronics that we're going to need in the device, minus the battery, of course. And what we can do now is we can actually run the logging and print that to the computer through a serial monitor and a serial plotter that allows us to view the sensor data in real time. So what I've got is I've printed out these two little manifolds here that would allow you to connect all of the air pressure sensors at once to the pitot tube over here. And so then that way, when we apply a pressure to the pitot tube or a velocity to the pitot tube, we'll be able to see how all the sensors respond with the same sort of pressure level on them. And that allows us to see which sensors are better than the others. So we've currently got hooked up an analog sensor. We've got the DLVR digital sensor, and we've got the Maytech ASPD 4525 digital sensor as well. Now, what we can do at first is basically identify how these go with an applied pressure by applying pressure through squeezing the tube. So if you have a look, if I grab this one's on the Maytech. If you watch what's happening on the screen, you'll see I apply pressure and we have a change in the pressure at the sensor. If I go and squeeze the other tube, it goes in the opposite direction. If I release fast, you can see quite a rapid thing. Now we're logging here at 100 hertz. That's 100 logs per second. That was about as fast as I could push my code. I'm sure if you were better at coding than me, you could push it quite a lot faster. But if you're much slower than this, you can see that when I do fast transient motions, that we would struggle to capture it effectively. So that's one of the reasons why we're logging at 100 hertz. So just to run through the other sensors, you'll see this is the DLVR going here. And that's the other side, the DLVR. And then this is the analog sensor, the 7002 DP pressure sensor. Now you'll note on the DP that if I go one way, I can max it out and cap it at 800 pascals compared to the other way where I can't. Now the reason for this is that the Teensy that I'm using here is a 5 volt tolerant board, but that is not equivalent to a 5 volt measurable board. So what that means is that this sensor over here is a 5 volt digital sensor. It outputs reading up to 5 volts on the output of it. It's running on the 5 volt rail. The Teensy will survive that 5 volts being applied, but when we start to max pressure, say the sensor wants to send a signal of 3.5 volts, the Teensy can only read up to 3.3 volts. So if we've got 3.5, 3.6 volts going in, the Teensy just thinks it's 3.3 volts. And that's when we see that flat plateau at the top. Of course, if we go the other way, if we're going differential pressure downwards, so applying the opposite direction, we can go all the way down to 0 and the Teensy will happily read that, which is why we max it out one way and not the other. Now currently I've got this outputting not just pressures, but also speeds. Specifically, I've got the speed coming from the Maytech airspeed sensor. In order to calculate that speed live, it needs to know the density, and that's where the BME 680 sensor comes in. Basically, when this device boots up, it will go read the ambient humidity, the ambient temperature, and the ambient atmospheric pressure, because it's fairly safe to assume that it will boot up with the device static. And then it will go through and it will calculate the current air density with those values. Once you have that air density, you can then, of course, use the pressures to work out your velocities. Over the course of a run on track, air density will obviously change, ambient temperature and pressure conditions change throughout the day, but it's going to be a pretty small change. And again, we're going to log all of this data, including the raw pressures and everything, so that you could go through in post-pro and apply some compensation stat using your data from the end of session as well as your data from the start of session, and then you can use that to work out what your compensation should be over the entire run. Now all of this data, like I said, is being logged. It's being logged to this micro SD card at the front. That is actually the slowest part of the entire process, which has meant I've had to do a lot of code optimization around getting that micro SD card to log quickly, and I found the biggest gain was actually in just slapping in the fastest micro SD card I could physically get into that slot, and that made my logging rate jump massively from around about 10 hertz max all the way to 100 hertz. So now for a little demo, what I've got is I've got a hairdryer here, and so what we're going to do is we're going to make some wind with this hairdryer. So I can go and grab my pitot tube. And we'll just try going for a slightly different nozzle profile, just to fill out the air a bit more. And of course we can compare all the readings for speeds we're getting against the GPS unit over here, Matex GPS unit there, and that will allow us to work out things like headwind or something like that. So by this point you've probably noticed that I've got 3 pressure sensors hooked up here, while the yaw probe itself only requires 2 pressure sensors. The reason for this was so that I could have a look at 3 different levels and types of pressure sensor, so I could try and work out whether one was better than the other or how they were generally responding. So when we look at the log file for the data that we've just plotted then, what we can see is how the sensors are behaving with respect to each other. So you'll see these little blips at the start are when I was squeezing the tubes to demonstrate for you how it's going on. And you can see that when we zoom in a little bit more on these things, they're actually a lot better resolved than what the serial monitor was sort of showing, because we can actually zoom in and have a look statically at how this stuff looks. If we just have a look at the 3 different sensors here, you can see what happens when I've squeezed the 3 different tubes, and they all behave fairly similarly. Obviously the absolute values are a little bit different, but you'd expect that because I'm squeezing tubes to different levels. Now the thing that more interested us is how they behave when they are all together. What we have here is we have the bit where we were actually blowing it with the hairdryer. And the first thing I want you to notice is the fact that the green trace, which was the DLVR, is much better zeroed. Now, I expected with the analog sensor there'd be a pretty significant offset. The datasheet for that sensor says that it's plus or minus 0.1 volts, which is not insignificant and is the sort of offset that we're seeing here. I was a bit more surprised that the MS4525 in blue had such a large offset from 0 with nothing going through it. So that's the sort of thing where given it's a digital sensor, I would have thought the offset would be much tighter. But anyway, on the offset, certainly the DLVR seems to be the champion. And while we obviously have a sample size of 1 for each of these sensors, it's worth noting that the common opinion on these sensors is that the DLVR seems to be the higher end option. So the other thing that you'll notice in these signals is that the analog one and the 4525 are both pretty noisy compared to the DLVR, which is a much less noisy curve. And also the analog and the 4525 seem to have fairly large steps on them. Now the analog, I understand why, because the standard ADC default input on the Teensy is 10-bit analog to digital conversion with option to 12-bit, whereas the DLVR runs at a 14-bit. But theoretically, the 4525 also runs at 14-bit, so maybe that's just not enabled in my libraries. But either way, looking at the general noise characteristics and all that, I think the DLVR would be my choice and is probably the sensor I would use going forward. It's worth noting too that the DLVR also comes in a DLHR variant that is a 16-bit conversion, so even more accuracy there, although to be honest with you, I think that the 14-bit is probably quite ample for the sort of work that we're doing. So looking at the pressure profiles, when we blow on all of them, you can see that they actually all resolve everything pretty much the same. We've all got the same rough trends, even at what's actually quite a low speed of a hairdryer blowing on them. And you can see that the initial offset is basically reflected at the offset where they're sitting down. Again, though, you can see that in these plots that the DLVR just looks like it's that little bit less noisy and more consistent than the other 2 sensors, which is something that I would probably go for. Looking at the transient response, when I was flickering the hairdryer over the pitot tube, you can see that the transient response on all of these is not super well resolved, courtesy of only being at 100 hertz. Ideally, we would be at like 250 hertz, but we work with my coding ability there. If you just pull the offset out of it, you can see that the trends match very closely, and any difference in response beyond that is probably down to the tubing and the tubing sizes in general, rather than just the sensors by themselves. So I think either of these sensors would probably work quite well for this project, but if I was to make a new one from scratch, I'd just grab 2 DLVRs and call it a day at that point. In case you were wondering how that looks on a more overlaid level, I've put in some offsets now to make sure everything is zeroed. So you can see that what we've got here is that everything is sitting around the 0 mark here, and you can really see that extra noise on the green and the orange traces versus the blue DLVR trace there. And let's just have a look at the response to the hairdryer. So that's a big long hairdryer burst. One thing you'll notice is that the DLVR is reading a lower pressure here than the other sensors. Now I think this is something that we'll have to take a look at in the full speed testing to see whether or not that is the more or less accurate of the sensors, because obviously we've got 3 sensors here that are all slightly disagreeing. So the easiest way to see what that's like is to actually measure it. So the way that I'm going to do that is I've got the GPS unit hooked onto there. So we'll go GPS speed on a wind-free day, go out logging and see how close we are to the real airspeed. And then that will tell us which one of the sensors is the most accurate on the pitot tube. And then just having a look at the transients to see how it gets resolved in the transient, you'll again see that DLVR is reading that little bit lower than the other sensors yet again, but the response times of all the sensors are pretty similar. These up and down traces as I was flicking that blow dryer across it at high speed are all very similar response times. As a closing side note, videos like this cost more to produce than what they earn through ads, so if you could support the channel by either going to the Patreon, buying a JKF Aero course would be great, or even just sharing this video and getting the word out there, I would greatly appreciate it. So anyway, that's all for part 2. Hopefully you enjoyed it, and maybe I'll see you in the next 3 years when we're finally putting this thing actually together on the car.